So when it comes to roots, there might be certain things that you already know. There might be certain things that will be new to you. Uh, there's different techniques to be working with roots. In the beginning of this lesson, it's quite unified how you go about things, but as you proceed and as you go through more and more questions, there's different ways to get to the same result. You want to look for the quickest way to actually get the job done is one thing I'll say to you. All right, so let's go ahead and start very simple, and let's take question number 8 here. Question number 8 here says, what's the fourth root of 16? Okay, so one of the things that you want to think about is what number times itself 4 times, right? You multiply it once, twice, 3 times, 4 times, and you end up with the number 16, right? If you can do that in your head, that would be awesome. If you cannot do it in your head, here is just something to help you out. These are just training wheels at the moment, but we try to leave the training wheels as quick as possible. Is what you can do is you can make a factor tree, right? So you see me making a factor tree here. And after you make that factor tree, you can write down, well, that's 2 times 2 times 2 times 2. That gives me 16, right? So what we're really saying is the fourth root of 16 is the same thing as the fourth root of 2 times itself 4 times, right? So one nice technique to do this is to say I'm looking for sets of 4, right? So here is a single set of 4 2's, right? So what you do is you essentially take this 2 out of the picture and you ask yourself, what's left, right? What is left after I do something like that? And if you look carefully, there is nothing left, right? Everything is gone. And because there's nothing left inside of that fourth root, this means that the answer to the question is 2, all right? And if you didn't understand that example, I have several more. So let's try number 10 here. Number 10 says the third root of -1, right? So we don't really need to make a factor tree for this if you think about it. So what number times itself 3 times gives you -1, right? Think about that. So the answer to this is -1. All right, if you think about it in your mind, -1 times -1 times -1 gives you -1. And you see you did that 3 times. And so that means that the answer to this question is -1. All right, let's take a look at number 12. Number 12 says, find the third root of 54. All right, so find the third root of 54. Okay, very good. Let's go ahead and try this one, inshallah. The third root of 54, there are 2 ways to go through this, okay? Right? There is method 1, which is the quicker way, and the way that you really want to stick to in the long run. And there's method 2, which is not the quicker way, all right? It's the slower way, and you want to avoid this method, but in the beginning, it's the one that we generally use just to help with understanding. Okay, so the quicker way is to say this. The quicker way is to say, can I rewrite the number 54 so that it's got at least one perfect third root, right? Can I write this in a way so that it's got at least one perfect third root, right? Is there any number out there, right? And you'll excuse me, and you'll end up with um, not necessarily 54, but you'll end up with 2 numbers that multiply to 54, and one of them has a perfect third root, right? So if you think about it, you can rewrite third root of 54 as third root of 2 times the third root of 27, right? And 2 times 27 is 54, so the third root of 2 and the third root of 27 is something that we can break 54 up into. And then you can say, well, this part right here has a perfect third root, and the perfect third root of 27 is actually 3, right? Because 3 times 3 times 3 is 27. And so you can therefore say that the final answer is going to be 3 multiplied by the third root of 2. 3 multiplied by the third root of 2. All right? Now, usually that method right there, students, one of the reasons why they struggle with it is because they're not very good with thinking as quick, especially in the beginning, okay? So you'll catch on to it eventually. So here is the slightly slower way of doing it. What you do is you say, okay, I'm going to make a factor tree for 54, right? So 2 times 27. You're really going through that same idea, but you're going through it slower just to convince yourself. 3 and 9, 3 and 3, right? And then you say 2 times 3 times 3 times 3 gives me 54, all right? So what we're really saying is the third root of 54 can be rewritten, and this is how we did number 8, right? It can be rewritten as the third root of 2 times 3 times 3 times 3. Now, we are looking for sets of 3. So anything that you can make a set of 3 out of it, right? There's 3 of a kind. You can pull that out of the third root, right? So we go looking through this 4 numbers, and we notice that there is a set that you can pull out from there. And when you pull that out, right, when you pull it out like this over here, here's what you end up with. You end up with 3 multiplied by the third root of whatever is left over. And you always ask yourself, what's left, right? When I pull everything out, what is left over? And what's left over is just the number 2, right? So you leave that number 2 inside, and notice again that you've come to the same exact conclusion as you did earlier. It just takes a lot longer to complete that question. All right? All right, let's try number 14. Okay? So the fourth root of 48, x to the power of 5. Number 14 says the fourth root of 48, x to the power of 5. You're welcome to pause this video and try to do this by yourself, inshallah. But here is the quicker way to do it. I'll call it M1, right? The quicker way to do it is to say, well, the number 48 can be broken down into 3 and 16. And if I can break it down into 3 and 16, the fourth root of 48, x to the power of 5, can be rewritten as the fourth root of 16 multiplied by the fourth root of 3, x to the power of 5. We'll deal with the x to the power of 5 in a moment, right? But then what that'll do for you is if you go back to the result from number 8, you'll notice that we've already done the fourth root of 16. We know that the answer to that right there is actually a 2. So as far as the numbers are concerned, we've simplified that a little bit. And then if you think about the x's, right? This is a lot easier than you would imagine. So you basically have, just imagine this, you have 5 x's, right? They're multiplied to one another, and that's what x to the power of 5 does. And you're trying to find a fourth root of 5 x's, right? So the logic that we used in the other method is we said, well, you're looking for sets of 4. This can all be done in your head, by the way, right? So you're looking for sets of 4. And so here's a single x that you can pull out of this picture, right? So when you pull this x out, then you ask yourself what's left over, right? And so whatever's left over is going to remain on the inside. And so therefore, the x comes out, right? So we're talking about this right here. The x comes out like this, and what's left over is a fourth root of 3, because the 3 is still there, right? The 3 hasn't left, and then 3x, right? So there's still a x left over, there's still a 3 left over, and so they remain inside of the fourth root. Oftentimes, a common mistake that students make is they forget to write the root. Okay, what do I mean by that? The root is a fourth root. You always need to write that. Think about it. That was your directions. That's what told you what to do. If you leave that out of your answer, that's technically the wrong answer. All right? Now, let's do this in a second method. As I said, usually the first method does not make sense to new learners or people who have forgotten how roots work. So let's talk about the second method. I do the first method first, even though it tends to confuse people, because it's the quicker way and it's the one we need you to learn really how you really carry forward. That's how it's really done. This other method is more of a middle school way of going about it. So let's go ahead and start. Basically what we say is the number 48, what can you break it down into? All right, so the number 48, 3 and 16, right? 4 and 4, and then 2 and 2, right? So what we're really saying is the fourth root of 48, x to the power of 5, can be rewritten as the fourth root. Notice how I always write down that it's the fourth root, right? The fourth root of 3 times 2 times 2 times 2 times 2 times 5x's. Now those 5x's, we just dealt with that a moment ago, right? So that's not unfamiliar to us. And again, you ask yourself, what am I looking for? I'm looking for sets of 4, all right? I'm looking for sets of 4. And here's a set of 4 2's. So I'm going to write out a 2. And I always get the question, where does that thing go? That thing goes on the outside. It's going to get multiplied to the rest of the problem now. Okay, the 2 goes out. And then the x also goes out, right? The x also goes out. There's a single x you can take out of the picture. And then you ask yourself, what's left over? I won't bother to write that piece now. So you'll have a 2 and an x outside, and a fourth root of whatever's left over. There is still a 3 that hasn't left, and there's still a single x that hasn't left, and therefore you write in that 3x right over here. Again, take a look at the answer on the left, take a look at the answer on the right. They are exactly the same answer. It just, you know, they take different amounts of time to complete, as I said. All right, we're going to try a couple more here. Number 16. I think you guys are in good shape to pause this video if you like and try number 16 by yourself. Variables are actually a lot easier to deal with than numbers when it comes to roots, because think about it, you've got 10 x's, right? I'm not going to write them all out, right? But think about it, you've got 10 x's, right? And you've got 5 y's. And you always ask yourself, I'm looking for sets of what? You are looking for sets of what? Sets of 5, right? So how many sets of 5 can you make out of 10 x's? You can make 2 such sets, and they would leave. And when they leave, you have an x and an x. And actually, you know what? I think for this part, it's probably best to, because now there's 2 sets that are leaving, and you might say, you know, how are you supposed to deal with that? So let me draw for you 5, 6, 7, 8, 9, 10. Yeah, as you can see, the long method is quite ridiculous when it comes to higher level math. And that's why you want to avoid this as much as possible. But inshallah, this is just as a demonstrative purpose that I'm doing this for you, right? So here is the first set of x's, 5 x's. Here is the next set of x's. That's another 5 x's. And here is a set of 5 y's. So guess what? Everything leaves. But the reason why I just did this for you is because normally the question is, wait, what am I supposed to do with those 2 x's? You're supposed to multiply by them, right? So x times x is going to give you x squared. And then what's left over from the x's? Nothing. And then sorry, I wrote the number 5 here. I meant to write y. So y leaves from the other part of the sets, and so the x squared y is what comes out. And guess what? There is nothing left over. All right, there's nothing left inside. Well, what do you do when there's nothing left inside? Basically, what you do is you don't. This looks ridiculous if you write fifth root of nothing, right? If like write a 1 or something like that. Don't write 0 because then that's wrong. You just leave it. Okay, just leave it. Don't write the fifth root, and just write that as your answer and move on. Now, what's the trick here? What's the trick here? Do we really need to write out 10 x's and 5 y's? No, not really. Okay. What you can simply do is you can think about the fact that if you've got 10 x's and you're looking for sets of 5, 10 divided by 5 is 2, and so that's why we end up with x squared. All right? Let me say that again. If you've got 5 y's and you're looking for sets of 5, 5 divided by 5 is 1, and that's why you pull out a single y. Okay? So the secret is to just divide out, right? So let's do one more in this set, and inshallah we'll move on to the next piece of the lesson. Number 18 says the third root of 3xy squared over 81 x to the power of 4 y squared. So one of the things that you realize is you need to deal with what's on the inside first, right? So what I'm going to do here is I'm going to forget about the fact that this is a third root. I'm going to just leave that for a moment, okay? And we'll just focus on the inside here. Okay, let's talk about that. All right, let's just talk about the inside. If I simply gave you this fraction, right? If I gave you this fraction, hey, look, I've got 3xy squared, and I've got 81 x4 y squared. Can you simplify that for me, right? Can you simplify this fraction for me? So one of the things that you can say is, well, how about the 3 and the 81 make a 1 and a 27, because 3 goes into 3 once, and 3 goes into 81 27 times, so that'll take care of itself. Then the x and the x to the power of 4, you can simplify those, and you can say that'll become x cubed. So what are we getting right now? We're getting a 1 in the top, a 27, right? And then the x's are gone from the top. There's 3 x's remaining in the bottom. And finally, if you look at the y's, well, they're all entirely gone, and so they don't show up in our expression. Now let's bring this problem back to roots. Okay, let's bring this problem back to the roots. So you have to be a little bit clever in dealing with that part of the question. If you bring it back to the root, you'll be like, okay, so this is the third root of, let me make that a little larger. Actually, you know what, let's write it over here. So the third root of 1 over 27x cubed. Now, if you didn't know this rule about roots, or if you forgot it, then please listen carefully, all right? So the way that's going to look like is the third root of 1 over the third root of 27x cubed, right? So the rule, in the algebraic rule, basically, I'll write it for you in green, says if you have the nth root of a over b, that's the same thing as the nth root of a divided by the nth root of b, right? So just kind of remember that little rule right there. So having done that, you got to ask yourself, what's the third root of 1? Meaning what times itself 3 times gives you 1, and the answer to that piece is simply 1. It's 1, right? And what's the third root of 27? The third root of 27, we discussed this earlier, is 3. And what's the third root of x cubed? Again, if you have 3 x's written out, how many sets of 3 could you make? You could make a single set of 3. So 1 over 3x is how you would do it. For anybody who's struggling to understand how did you do that so quickly, because I know it's a new way of thinking for some of us, so what you can think about it is like this. So I thought about 27x cubed to look like that, and I made a factor tree in my mind, right? To figure out what 27 multiplies to, what multiplies to 27. So 3 3's multiply to 27. So there is a set of 3 that leaves. Here's a set of 3 x's, all right? And those leave. And so what you think about is now there's only a 1 left inside of the third root. So this becomes a 3x, and you don't bother to write the third root of 1. You just leave that part out. You just say 3x, and that's why it looks like the way that it does. All right? So that's the first objective. Inshallah, the odd questions I have given to you to try, and I will eventually post the solutions to them as well. All right? Now, let's move on to another piece of the lesson. And in this, what we're going to do is a little bit beyond simply simplifying the expressions. All right, there's a little bit more that's happening here. So before we do that, let's just take this one remaining guy, which is 9x to the power of 5, and think about it this way, right? You've got the square root, right? One thing about the square root is it's got a second root that we don't bother to write, right? It's understood as a notation in the mathematical community, but really it's 3 times 3 times 5x's. All right, this is the last time I do it this way, but you got 5x's, and if you want to make sets of 2, right, you're making sets of 2. Here's a 3 that leaves, here's an x that leaves, here's another x that leaves, and notice how there's still an x remaining. So what really happens is the 3 multiplies to the x, so that's really 3x squared that all come outside, and you're left over with the second root of x still on the inside. Okay? So there's that. Now, let's move over to number 22. For number 22, we'll write down the question, but it requires a little bit more thought before we get started with that question. Here you've got 2 roots, right? Now, what I want to ask you is what's happening between these 2 roots? How do you read this, right? What does this mean? It says root 5x, and right next to it says root 20x cubed. If you don't know, what's really happening is these 2 roots are being multiplied. Okay, they're being multiplied. When you write something next to another number or of expression in algebra, that means those 2 expressions are being multiplied. So those are being multiplied. Now, if you do not know the rules for multiplying roots, a lot of people do forget them. Okay, so let's do a small little lesson on multiplying roots. Okay? All right, what do you do when you need to multiply roots? Let's suppose that you had an nth root of x and an nth root of y. Okay? Initially, this is a bit abstract, but you start to understand what's going on. Then what you could do is you can multiply the x's and the y's, all right? You can multiply the x and the y, and you can write this as an nth root. That's what the rule says, all right? Now, let's suppose if you had an nth root of x, but you had a mth, right? It's a weird thing to say, but the mth root of y. Now, can you multiply them? These cannot be multiplied. They cannot be multiplied. What am I trying to say to you here? All right, what's the rule? The rule is the roots must be the same. All right, so roots must be same. If the roots are not the same, you cannot multiply what's on the inside. So as long as the roots here are the same, n and n, you can make that the n root. If they are not the same, all right, this one's an n, all right, and the other one is an m, that's why the problem wasn't happening. You can try to simplify them individually and see where that would go, but you cannot multiply what is on the inside of each root. All right, so that's the idea. So having said that, you ask yourself, are the roots the same? Okay, are the roots the same? All right, and very quickly you realize, yeah, because this first one has a second root and the second one has a second root. So you can go ahead and by all means multiply them, right? So when you multiply them, you end up with still the second root. Okay, it's still the second root. 5 times 20 is 100, and x times x cubed is x to the power of 4. Now, this is a whole lot easier if you think about it. 100, again, try to avoid making factor trees for this. 100 has a perfect root. It's actually 10. 10 times 10 is 100, right? So we take care of that. If you didn't see that coming, then you would need to break this down into its factor tree, the number 100, and realize that it's 2 times 2 times 5 times 5, and then you would make sets of 2 from the 2, sets of 2 from the 5, then multiply the 2 and the 5 and get 10, right? But try to avoid that, right? The perfect root of 100 is 10. Now, the perfect root of x to the power of 4, or if you want to say the second root of x to the power of 4, is simply x squared, because if you've got 4 x's and you want to make sets of 2 out of them, that's going to lead to 2 sets, i.e. x squared. If you want to be convinced of it, by all means, pause the video and try it the long way, right? The one that we detailed above. Try it the long way. But we want to avoid doing that because now we're trying to learn multiplication here. So the correct answer is going to be 10x squared. All right. What we're going to do is we're going to first try number 26, okay? And then we'll come back to number 24 because 24 is a little bit harder, 26 is a little bit easier. So let's try number 26 first. All right, so number 26, it says that you've got 5 multiplied by the root of 8 and then negative 3 multiplied by the root of 3. Okay, now what do you do in this situation over here? So again, I'm going to go back to my drawing board here where it comes to the rules and just how you actually are supposed to multiply roots. And what I'm going to do is I'm going to write for you 2 roots here. I'm going to write down a times the nth root of x multiplied by b times the mth root of y. Okay? What do you do in that situation? Oops, sorry. It's not supposed to be the mth root of y. It's still the nth root of y. I apologize. Okay, so nth root of y. So first you have to realize that you can actually go ahead and you can multiply in inside of the roots because this is an nth root, that is an nth root. Using this rule that we earlier detailed, you can go ahead and multiply the x and the y, right? But the question is, what do you do with the a and the b, right? So what I'm trying to say here is the x and the y can be written as nth root of xy. But what do you do with the a and the b? You may have guessed it. The a and the b, they multiply, but they stay on the outside, right? So this is what that rule says. It's going to really look like that. Okay, now having said that, if you tend to get confused about things, what I would recommend is you remember this little tidbit, is you basically multiply the outers, okay, multiply the outers, and then multiply the inners. But don't cross them over, okay? Don't cross them over. Don't multiply an a to a y. It's not like a distributive property in that sense, okay? It's slightly different than that. So now, having said that, take a look at number 26, right? And see how that rule applies now. So I'm going to go ahead and I'm going to multiply 5 and negative 3 because they are on the outside of those roots. And I'm going to get negative 15. Now, before you multiply the roots, you got to ask yourself, are they the same root? This is the second root. This is the second root. So they are exactly the same roots. So now what you can say is, yes, I'm allowed, right? I'm allowed by this top rule to actually multiply them. So when you multiply the insides, you end up with the second root of 8 times 3, which is 24. Okay? So here is where we're sitting. But this is one of the reasons why the lesson is difficult, is because you don't stop there. You look at it again and you're like, can I break this further? And it turns out, now I'm going to use the long method to break this down, but you may stop and you may make a factor tree out of this if you wish, right? And look at my factor tree. And then you can say, all right, 24 is really 3 2's and a 3, right? So negative 15 multiplied by the root of 4 and the root of 6. That's the quicker way of doing it, okay? And then I can say negative 15 is multiplied by the perfect root of 4, which is 2. So negative 15 times 2 times the root of 6. So the answer is negative 30 root 6 in the end. If you wanted, you could have done this in the longer way, and you would have said the same exact thing I did, because you would have taken 2 of the 2's and brought them outside, as I did here, and the 2 and the 3 here would have been left inside, as 2 times 3 gives you 6, so that's how I ended up with the root of 6 still. So, quite a lot happening there. You'll catch on to it eventually. But let's do one more in this set, which is number 24. It says you've got the third root of 3, the second root of 10, and they're to the power of 4. All right, so the third root of 3, the second root of 10, and they're multiplied by themselves 4 times. Okay. Now, first off, ask yourself, can you multiply the 3 and the 10? Right? Can you multiply the 3 and the 10? And the answer should be no. You can't multiply them. And why can't you multiply them? Because of the rule that we detailed above. They need to have the same root for you to be allowed to multiply the inside. So that's not happening, right? So you can't multiply the 3 and the 10, but what you can do is you can try to see what this power of 4 will do for you. And so we can write this as third root of 3, root of 10, times third root of 3, root of 10. All right, that's twice. Third root of 3, root of 10. That's 3 times. Third root of 3, root 10. And that's 4 times. So I just wrote out the same expression 4 times. And that is one of the basic understanding of exponents. Whenever you have an exponent on something, that means whatever it may be inside, it's being multiplied to itself that number of times. So 1, 2, 3, and 4. All right, we wrote it out 4 times. Thank God it only said 4, because if it said more than that, we would have to written out this many times as well. Okay, now, what I'm going to do is I'm going to take the roots of 3. Okay, it's more a thought than anything. I'm going to take the roots of 3, this one right here, the third one, and the fourth one, right? And I'm going to write them next to one another, because remember, everything is being multiplied anyway. So the third root of 3, I'm going to write those all next to one another like this. And then I'm going to use the same exact logic, and I'm going to write down the roots of 10 next to one another. All right? Yes, things are still being multiplied, but I just shuffled them around so I can multiply them in another order. If you're wondering how can you possibly do that, you're definitely allowed to do it, because 3 times 2 is 6, and 2 times 3 is also 6, right? So you can shuffle things around in multiplication. You'll still get the same answer, right? That's your understanding of algebra right there. All right, now, what am I going to do here? Remember that first rule that we talked about. If it's the same root, you may go ahead and multiply what's on the inside of the root. So having said that, notice that now this is a third root, this is a third root, this is a third root, and this is a third root. So technically speaking, I can go ahead and say this is the third root of what was on the inside. 3 times 3 times 3 times 3. All right? And I can use that same logic for these 10s, right? I can use the same logic because they all have the second root. So I'm going to go ahead and multiply all of those 10s and still give them their second root. So 10 times 10 times 10 times 10. And if you're wondering why are you not multiplying, and look, notice how I left a second root there, okay? Now if you're wondering why are you not multiplying them, why don't you just like make this 3 times 3 times 3 times 3, which is 81, and then 10 times 10, which is 100, times 10, which is 1,000, times 10, which is 10,000. It's because that you don't want to make the expression longer. You want to make this shorter. So you're looking at its prime factors. You're looking for sets of 3, right? So here's a set of 3, so they can leave. And for this one, you're looking for sets of 2. Notice how, as this lesson is moving forward, it becomes kind of a gray area. Which method are you supposed to use? It just comes with experience. Which one are you going to use? Which one is the quicker technique? Otherwise, some people might actually multiply all of those tens that you see over there and be like, okay, great, now I'm stuck, right? So now notice how you can make 2 sets of 10 here and 10 here. If you're wondering why didn't you do the same thing here, it's because we were not looking for sets of 2s. Once again, we were looking for sets of 3s, right? So if you got a 10 and a 10, recall that you're supposed to multiply these two, right? You multiply the both of those, and then there's nothing left inside of that second set, right? So you end up with 3 third root of 3. And on the other end, you're basically, right, so this is being multiplied to 10 times 10, and 10 times 10 is 100 times 100, right? Again, when there's nothing left inside of a root, you don't bother to write it, right? Everything left. So then you ask yourself, okay, what am I supposed to do with this? You're supposed to take the outers and multiply by the outers, so the 3 and the 100, you can multiply those and say the answer is 300, and then write it next to third root of 3, right? Because there is no other roots over on the other side. Now, please remember the one little comment that I made, that a common mistake students tend to do is they forget, where did I write this? I wrote it over here, and now I can't really find it. But one of the common mistakes that students tend to make is they forget right over here to write the root. Okay, they forget to write the root. So please don't make that common mistake. Remember to always write the root. Okay, now the last objective of this lesson, is to learn to add and subtract, right? To add and subtract roots. That one is a little bit different. It involves a little bit more effort, all right? Now, the rules for multiplying roots are over here, okay? They all remain the same, right? When you need to add and subtract roots, what exactly are the rules then? So we're going to detail those in the corner, all right? So adding and subtracting roots. What do you do now? All right, so for this, I'm going to give you kind of a set of rules here. What you need to make sure, okay, make sure that the roots are same. The roots are same. And make sure that the radicands are same, right? If you don't know what a radicand is, it's the stuff that's inside of the root, okay? So now let me give you an example, okay? So if you had the nth root of x, and you had the mth root of y, and somebody asked you, now add or subtract these, you cannot do anything. Why can't you do anything? It's because, number one problem, they're not the same roots. All right? Not same roots. That's the number one reason why you can't. Number two reason is because the radicands, those are called the radicands, so they don't have the same radicands. And because of that, right, you may not actually add and subtract them. Okay, now let me give you another scenario. Let's suppose that you had the nth root of x, and you had the nth root of y. Now can you add or subtract them? No, you cannot. Okay? What's the problem now? The problem is the radicands are not the same. Okay, so it's quite restrictive in adding and subtracting uh, what you can add and subtract based on the rules. So now it's not the same radicand, and because of that, you got to leave it alone. You can't mess with it, right? I realize that the roots are the same. That's very nice, right? The roots are the same, but the radicands are not, so you got to leave it alone, all right? All right, scenario number 3. Let's suppose, and this is the one that students tend to get confused by, let's suppose that you have the nth root of x, all right, and the mth root of x. Now what's the problem? The problem is this time they don't have the same roots, not same roots. You see that? So these are all 3 cases, number 1, number 2, and number 3, where you can't actually do anything. You're just basically looking at it. It's very specific what needs to happen. You got to make sure the roots are the same, and you got to make sure the radicands are the same. Then and only then can you add and subtract what you're looking at over there. Okay? Number 28 says the 6th root of 5 minus the 4 root of 5. Right? So 6 multiplied by the root of 5, and then 4 multiplied by the root of 5. Well, check the rules, right? The rules say as long as the radicand are the same, so that's a check, all right? And then as long as the roots are the same, they're both the second root, so that's a check, you may go ahead and add and subtract. Now, if you're wondering what exactly am I supposed to add and subtract, maybe you learned this one, Bismillah with Sister Reem. So 6 minus 4 is 2. So this becomes 2 times the root of 5. Notice how the root of 5 stays exactly the same. Right? If you don't understand what I just did there, think of it this way. All right, this usually helps. Think of how if you had 6 times, no, actually, let me try it this way. If you had 6 times x minus, right, minus 4 times x. What's the like terms here? X's. And remember how you learned you combine like terms. So 6 minus 4 is 2, and the x still remains an x. So if you think about it like that, right, become a really good algebraic thinker. Notice how they basically show up this way. So when you have a root on it, well, guess what? This is just going to become the root of x. Think of it that way. All right? So that's why we keep the root 5 exactly the way it was. You don't actually subtract the inside, so don't make up that rule, right? Now, let's try number 30. All right? Number 30, initially, well, let's write it down first. 2 multiplied by the root of 12 minus 3 multiplied by the root of 27. Look, initially, what it seems like is, yeah, you can't do anything. I'm going to move on, right? But come on, that would be too easy, right? That would be too easy. What you really got to do is you got to stare at it long enough and say, okay, is there any way, considering how they are the same roots, right? They are both second roots. Is there any way I can depress these? I can simplify them into looking like the same root, right? And for that, you need to have a little bit of practice with that first objective of the lesson. What am I talking about? All the way at the beginning of the lesson, when we spent some time simplifying some of these roots, that's what you really got to get good with, right? And then at that stage, you can look at some of these questions here, right? The 2 root of 12, and you can say, all right, what if I called 2 multiplied root 12 as 2 multiplied by the root of 4 multiplied by the root of 3, right? It's because 4 times 3 is 12, so 12 can be broken down that way. And what if I changed root of 27 into the root of 9 times the root of 3? Now let me pause here. If that understanding is not coming to you, if you're like, wait, how did you just do that? Then pause the video, take the number 12, take the number 27, and go ahead and break them down, okay? 3 and 4, 3 and 9, 2 and 2, 3 and 3. So all of this thinking, we don't have time to keep writing those steps, so we don't bother to show them necessarily. But when I said 12 is root 4, root 3, this is what I was talking about. If you were to write 12 out, you would have had 2 times 2 times 3. And if you had written 27 out, it would have been 3 times 3 times 3, right? And that's how I ended up with what I have here, right? Now, if you look at the root of 4, the root of 4 is actually 2. So you have 2 times root of 3, and you have 3, and the root of 9 is also 3. So 3 times the root of 3. So this becomes 4 root 3 minus 9 root 3. And now let's pause and let's look at the rules. The rules say make sure that the roots are the same. Yes, they were same from the beginning. They were both the second root. And make sure that the radicands are the same. Now the radicands are the same. This is a 3, and that's also a 3. So when the inside is the same, you may go ahead and you may do what the outside is telling you to do. So 4 minus 9 gives you a negative 5. So the answer to this question will be negative 5, the root of 3, like that. Okay? Now, let's take number 32 here. All right, number 32. It says the root of 5 minus 2 times the root of 5 plus 3. Okay, root of 5 minus 2 times the root of 5 plus 3. That's what we're looking at there. All right, now what do you do in this situation? Well, first off, notice that there is 4 terms. 1, 2, 3, and 4. Now, the first 2 terms are being subtracted, and the second 2 terms are being added, right? So let me get rid of this highlighting. That might confuse things, right? So the first 2 terms are being subtracted. The next 2 terms are being added. Not just that, what's happening between this set and that set? They are both being multiplied, all right? They're both being multiplied. So in fact, what we really need to do here is we got to use the FOIL method, all right, or the rainbow method, whatever you call it. We got to multiply the root 5 into the 3. And so we have to multiply the root 5 into the root 5 into the 3. And then we have to multiply the 2 into both of those as well, right? So here's what that's really going to look like. I'm going to write the whole thing out. When you multiply root 5 and root 5, here is what it looks like. Root 5 times root 5, okay? When you multiply root 5 and 3, all right, you can't multiply the 5 and the 3 because the 3 is not inside of a root, right? So you have to write it as 3 root 5, like that. Okay? Now let's go to the next piece. You're going to take negative 2 and multiply it to root of 5. So that becomes minus 2 root 5. And you're going to take the negative 2 and multiply it to the 3. So that becomes minus 2 times 3. All right? Now, simplify this a little bit. You end up with the following. You may remember from geometry a little bit that the root of 5 times the root of 5 gives you 5. Now, why is that? It's because, look, they have the same exact root. And in multiplying roots, I know it's a lot of rules, but in multiplying roots, as long as the root is the same, you may multiply what's on the inside, right? That's why that used to happen, where if you multiply the root of 5 and the root of 5, it's actually the root of 25. But then the root of 25 is what? It's 5. That's why we say the root of 5 times the root of 5 would just give you 5, right? That's the thought process that we're following there. Now, that second piece, look at it carefully. This is the addition and subtraction rules, right? Because, number 1, the roots are the same. Number 2, the radicands are the same. So you may go ahead and follow the rule. Just take a look at how we did it in number 28. You may follow the rule for addition and subtraction of roots, and you may say that this is going to give you 3, positive 3 minus 2. So it'll give you 3 minus 2, which is 1, and then the root of 5. And finally, if you look at this piece right here, that's going to give you a 6. So you'll have a minus 6. Simplify that a little bit, and you end up with negative 1, because 5 minus 6 is a negative 1, plus a root of 5. And once again, we are done with this question right here. Okay? In number 34, it says 9 multiplied by the third root of 24. You now know enough where if you wanted, you could pause this video, right, and try this by yourself and just be more convinced of it. So 9 multiplied by the third root of 24 minus the third root of 81. Okay? All right, so first off, let's break 24 down, right? 24 is 2 and 12, 2 and 6, 2 and 3. So if you were to make sets of 3 out of that, you would get a set of 3 2's, and the 2's can come out. But what remains on the inside is that 3. So by all means, pause the video and try it by yourself, but you'll have 9 multiplied by 2 times the third root of 3. Okay? Now the other piece is going to be 81. 81 breaks down into 3 and 27. You could have also said 9 and 9. I just tend to start with a small number. 3 and 9, and then 3 and 3. So this right here gives you 4 3's. Right? It gives you 4 3's. So if you make sets of 3 out of that, that's a single set of 3 3's that you can make. And so this other piece will look like the following. You'll have 3 times the third root of what's left over. When you're done with this, what's left over is that final 3. It stays on the inside, and so it's going to become the third root of 3. Now, before we add and subtract, notice that there's a 9 here and a 2 here. They multiply to one another, and you end up with 18 third root of 3 minus 3 times third root of 3, like this, right? And now you follow what the rule says. 18 minus 3 is 15, and the third root of 3 is simply copied. Why was I allowed to do that? Once again, because when the roots are the same and the radicans are the same, I may go ahead and add and subtract as I wish. Number 36. One of the things it says is whatever this expression is, it's squared. So I want you to think about what we said earlier about how whatever exponent is up there, that means that's the number of times you multiply that certain piece that's on the inside. So when it says root of x plus the root of 5 whole squared, what that really means is that you're going to be writing it out twice. Number 36, you're going to write down the root of x plus the root of 5. All right? That is what it said, right? Yeah. Okay. Now, we're going to go ahead and rewrite this as the root of x plus the root of 5 multiplied by the root of x plus the root of 5. Right? So I had said this earlier, and I'm saying it again, is because it had a square on it, we wrote it out twice, like this over here. Right? Now you use a similar method as we used in number 32, and you use the FOIL method, and you're going to be multiplying the root of x times the root of x, and you're going to multiply the root of x times the root of 5. Okay, so that's the whole point in that first piece. Then you're going to multiply the root of 5, the root of 5 to the root of x, and then the root of 5 to the root of 5. So that's the FOIL method for you. Okay, so here's what that's going to look like. Root of x times root of x. That's the first term. Then root of 5 times root of x. I know that technically we're multiplying the root of x to the root of 5, but we tend to write the numbers before and the variables later. Then when we go from the root of 5 to the root of x, that again is going to look like root of 5 times the root of x. And finally, the root of 5 times the root of 5. They all have addition signs, so that's nice. And so that looks like that right there. Now, let's simplify these. That is really the root of x times x, so that's going to give you x. This right here on the right hand side, right, a root of 5 times root of 5 will give you 5. So that takes care of those. Now if you think about these terms, can you multiply the root of 5 and the root of x, right? The rule says as long as you have the same root, right? Not the same radicand, but as long as you have the same root, these are both second roots, you are allowed to multiply them and make root of 5x and root of 5x. All right? Now we're going to have x plus root of 5x plus the root of 5x actually gives you 2 root of 5x's. Right? Remember the addition rule for roots, as long as the radicand are the same and the roots are the same, you may add the exponents. The exponents were 1 and 1, so that's how I ended up with the 2 root 5x. And finally, at the other end, we have the number added 5. There is not much you can actually do with this. This is just as far as it goes, so you have to leave it to that. Now let's try number 36 again. All right, we want to try number 36 again, but what we want to do is we want to talk about a formula. All right, so here's number 36 again. There's nothing wrong with the one that we did previously. I just need you to learn a certain technique and a certain formula. And the formula, in case you forgot it, is called the square of sums formula, because what you're doing is you're squaring a sum. Right? This one says that you have the first term squared plus 2 times the first term times the second term plus the second term squared. Oftentimes people call this the a plus b whole squared formula. Right? And if, by the way, if it says a minus b squared, then this would have looked exactly the same way except with the difference of the signs. So when there's an addition sign here, there's an addition sign here. When there's a subtraction sign here, there's a subtraction sign here. So having said that, this will save us a little bit of time if we look at this question again, where it says root of x plus the root of 5 squared. You could say, okay, I'll call my term right here my a term, and I'll call that term right there the b term. So when we say a squared, what does that mean? What we're really saying is the root of x squared. Right? So let me write it right below. That really represents a squared. Then you write the addition sign, because there's an addition sign right there. Then you do 2 multiplied by the first term multiplied by the second term. And finally, you do the root of 5 squared, the last term squared. Now how does that fall into the formula? The formula says 2 times a times b plus b squared. So I simply wrote out a plus b whole squared in its formula, right? What I just showed you over here. I simply wrote that out, and I have a quicker way. Remember when I started this lesson, which was a while ago now, but I said make sure that you always find the quickest way to go about the question. All right, the quickest way. So the quickest way to go about it was the one that I just showed to you in 36 number 36 again, revisited really. And now you try to simplify it. So you ask yourself, what's the root of x squared, right? The root and the square, they cancel one another out. Or if you don't understand that thinking, then please realize that really means the root of x times the root of x, which means that would be an x. So you have an x. Then the root of x and the root of 5, you are definitely allowed to multiply them because they have what? They have the same roots. So you end up with 2 times the root of 5x. And finally, the root of 5 squared, again, is root 5 times root 5. But by that logic, you really end up with 5 because the root of 25 is 5. And once again, notice how that the answer that we got earlier, okay, the answer that we got earlier right here is the same answer that you get again. Okay, so that's one little piece that I wanted to mention. 4D here says the following. It says that you've got 3x times the root of 9y plus 4 times the root of 25y. Now what do you do? Okay, well, first off, what you have to think about is, are we even allowed to add and subtract, right? They do have the same exact roots, that's a check, but they don't have the exact same radicands, so that's not checked out. Now you can look at them and be like, well, could you possibly make the two radicands look the same? And where have we done that before? We've tried that technique in number 34. We've tried that technique in number 30 and 28, right? So we're just using that same exact logic, but this time we have variables on the inside. But let's go ahead and focus on the root of 9y. Now think to yourself, is there a perfect root of 9? And if it is, what is it? Right? So the answer that you should get is the perfect root of 9 is actually 3. So you end up with 3x times 3 root of y, because that y is not having a perfect root, so it needs to stay on the inside. Now let's look at the other one. Okay, let's look at the other one, which is the root of 25y. Well, does the root of 25, does 25 have a perfect root? Sorry. And so you end up with 4 times 5 root y, because the perfect root of 25 is 5, but the y, it cannot move out of that second root, so it needs to stay there. Well, here's what we're looking like. We've got 3x, oops, sorry, the 3x is multiplied to the 3, so you end up with 9x root y added to 4 times 5, which is 20, so 20 root y. Now, as much as we're happy that, okay, awesome, now we actually have radicals, the root and the radicand looking exactly the same, well, the problem is you can't actually add 9x and 20, can you now? All right, 9x and 20 are unlike terms. So what's the most you could do with this problem? You can do something called factorization. Okay, you can factorize, and this is the most you could do, right? You can factorize. And in factorization, you notice that the root of y is being repeated twice, right? It's being repeated twice. So what you can do is you can write down the root of y once like this, and then write down 9x plus 20. Or you could have written it as 9x plus 20 and then the root of y. Okay, so some textbooks, they write it that way. So I just wanted you to be very flexible in your understanding of this topic. Finally, we're going to do one last question, and we're going to wrap up with this lecture. Number 42. Actually, it turns out to be a relatively simple one. It says 8xy minus 25 minus the square root of 25x squared y squared. Okay, and then added to the third root of 8x cubed y cubed. So added to the third root of 8x cubed y cubed. Okay, well, this being that final one, let's try to find the quickest steps to actually get the problem done. Well, first off, ask yourself, 25, does it have a perfect root? Yes, it does. It's 5. What about x squared? What about y squared? Can you perfectly find second roots to them? You absolutely can. So this becomes 8xy minus the perfect root of 25 is 5. The perfect root of x squared is x, and the perfect root of y squared is y. So guess what? Everything comes out of this second root. All right, now let's try this last one over here. In this last one, what's the third root of 8? What's the perfect third root of 8, if it has one? And the answer is yes, it does have one. The perfect third root of 8, sorry, is 2. The perfect third root of x cubed and the perfect third root of y cubed is respectively x and it's y, right? So now if you look at the expression, you can actually do a little bit more with it. 8 minus 5 plus 2. Notice how x and y are all like terms, right? So 8 minus 5 is 3. 3 added to 2 is 5. So you end up with 5xy as your final answer to number 42. And we didn't have this discussion, but realized that they were not the same roots over here, so you couldn't have added and subtracted them anyway. And definitely they were not the same radicands. These were two different radicands inside, so you couldn't add them anyway, right? But what did we do? We tried simplifying. Okay, so simplify first is one of my most overarching advices when it comes to roots. Don't just look at the basic rule and say, why is this not working for me? Try to simplify it and then see where that would actually take you.